we can explain magnetic properties in terms of the orbital angular momentum of charged particles like the electrons, but that wasn't enough to fully explain the properties of the atom. So we have to postulate the existence of some other source of magnetism for the atom, and we said that's the electron spin. Okay, and so we said that for an electron, since there is no classical analog for spin angular momentum, we say that we're just going to assume that those operators for the spin angular momentum properties behave the same way as the orbital angular momentum in terms of the way they commute. So, in other words, we postulated that we can only know the magnitude of the spin angular momentum and one of the components. Just like we can only get the magnitude of the orbital angular momentum and one of its components, and we choose the z component as the one we want to know. Okay? Now, there is, in fact, one more thing we do need to consider. Because of the existence of spin, there is a thing called a spin-orbit interaction, and that's what we're going to focus on today. All right? Spin-orbit interaction has to do with the fact that, all right, if you have an electron going around a nucleus, okay, imagine you're an observer at the electron, okay, so imagine yourself sitting at the electron and you're looking out and you see the nucleus. What would the nucleus seem to be doing? Because you're moving around the nucleus, okay, like you're on Earth, right? The Earth's moving around the sun, correct? So you have an orbital motion of the Earth around the sun. But since you're on the Earth, by looking at the sun, what does it seem like what's going on? It's as if it's the sun that's going around you, right? Sun is setting, sun is rising. So because of the orbital motion of the electron, it's as if, okay, there's a positive charge that's orbiting the electron from the viewpoint of someone on the electron, right? So you can say then that the electron essentially feels a magnetic field from the nucleus because of its orbital motion around the nucleus. All right? So since the electron itself has an intrinsic magnetism due to its spin, okay, then depending on how the electron's spin is aligned with the orbital angular, with the magnetic field that seems to be feeling from the nucleus, okay, that could affect its potential energy. So we have to add one more term to our Hamiltonian. We need to add a term due to the potential energy of the interaction of the spin and orbital motion. Okay, so we say this is spin-orbit coupling. And so the potential energy term that we have to add, we call that as being due to spin-orbit interaction. We can think of that as some kind of an internal Zeeman effect. Remember, what was the Zeeman effect? That's a splitting of the spectral lines as a result of putting your atom between the poles of a magnet, right? So if you're subjecting your atom to an external magnetic field, you have that splitting of the lines. It's called the Zeeman effect. Well, this one is built into the atom. Just because you've got this electron with its own generating its own magnetic field by inherent magnetic field, and it's orbiting around a nucleus, which is a charged particle, it's going to feel as if there's a magnetic field from the nucleus. You have to add this extra potential energy term. Okay, so that interaction is known as spin-orbit interaction. So that leads to a splitting of energy levels, and that allows you to explain further. If you look at your the structure of your spectrum from atoms, there's really fine structures there, smaller splittings of the energy levels that you see in this spectrum that can be explained by spin-orbit interaction. When you get to very large atoms, okay, that becomes significant. For hydrogen, it's not very strong. When you get to sodium, for example, we're going to look at the sodium lab spectrum in the lab, and you'll see that transition, for example, from the 2p orbital to the 2s orbital of sodium. You'll see a splitting of the line. Instead of just seeing just one line, you'll see a significant split of that yellow line from sodium, and that's due to spin-orbit interaction.